Good afternoon and welcome to this webinar on Master Key Retaining Walls. I'll just start by starting the Master Series, and we'll see that we're using 2015-11 as our version number, and we'll just go straight into retaining walls. So Designer Suite and into retaining walls, and we'll just select our retaining walls. And I'm going to take a brand new file, so new file. I just give it my own name and say create new. And that is our default setting for a new retaining wall, with a toe and a heel and a stem, and we have a little bit of passive pressure, a lot of active pressure, and we also have our default surcharge on the wall. 27 kilonewton because we have a 2.7 meter heel at the moment and the 10 kilonewtons. So very straightforward. So what we're going to do, we're going to learn to use the software by just designing this 3 meter high wall. So the first thing I will do is I'll walk over from left to right. I'll go to my soil data and I'll just check that I have the basic defaults. Yes, 30-degree soil friction, 18 density, submerged ratio 0.6, over consolidation ratio, which is really only used when we go for at rest, but we'll not do that at the moment. And then the base soil, if the base soil is different, and we will ignore cohesion and keep that in our pocket for when we have problems. Back pressure 100 kilonewtons per meter squared. I will leave the front empty, which means it'll be the same. So soil data I'm happy with, and just to check my design code, I am going to actually work with EC7, which gives me EC2 concrete and EC6 masonry if I use it, and we will be working with the UK National Annex. You can customize that and add in your own annex details if you're using this outside the UK. So back to the wall data, and this is the basic parts. I'm going to go for a 250 thick wall, 3 meters high, and I will leave that value as a design process value. I will go with a 5-degree soil slope, so there we are, and I will not put any front or back slopes. If I wanted to have a slope in the front, I could do so, but we will keep it nice and regular, and likewise at the back. The front soil will not be sloping, and we will assume that we have 500 millimeters of front soil. We'll not be using a nib, but we will be using a water table. So by default this is set to 500, which pushes it underneath our base and means it's of no relevance. I'm a great believer in having at least 500 positive of water. We can see that everything is instantaneous. There's no analyze button. As I changed the values, it drew it on the screen. It modified my pressure diagrams and my bending moment diagram. Obviously it remains the same, but the capacity lines and everything. So yeah, the bending moment diagram would change because that's the applied, not the capacity. That is the capacity diagram. So what we now do is we continue with our basic dimensions, and I'm going to say that it is a 300 thick slab. So that works, and what I really want to do now is define from a stability point of view how long the toe and the heel are. So I'm going to pull my toe right the way down to something a bit smaller, around about 700, and now what I do is I shorten my heel until I get an unstable base, either due to sliding or overturning. And now we have, in fact, we've got both sliding and pressure at the same time, which means we're actually at quite a sweet spot. So 1600, which gives me 550. So if I made that 750 or 650, we might get a nice round figure, which gives me a soil pressure problem. So I will go with the 750 or 700. So 2550 meters base length. So that's the stability of the wall. Now what we need to look at is the strength of the wall, and at the moment I have got no warnings, and what that means is the reinforcement is working. So going to my reinforcement tab, I can see we've got 16s and 12s. Interface is the face against the main soil, and that is the face that resists the bending. So if I reduce that to 12s, I will see that I am now just at the base, and that's at the top of the base starting to fail. So I can go up to 12s at 125 or 12s at 100 to keep it nice and small and contained, or I could go up to the 16s at 150. So it's very straightforward, and I can probably decide to go for something like 10s at 200 on the outer face. Now what I want to do is look at the base, and of course the base, the top and bottom are used structurally. So it's the top reinforcement here and it's the bottom reinforcement here that's important. So base top, he's got 16s again. I'm going to try and drop down to the 12s. That works at 150, and on the base 12s at 150. So I might decide to make everything easy, we will keep to a 150 arrangement and put whatever reinforcement is required, and in this case it would be the 16s at 150. So a 150 arrangement of main steel. And the longitudinal steel, no, I don't like 175, and I will just put these up to 200s. And would I get away with 10s? I would. So there I go. That is my reinforced masonry wall designed in about 7 minutes from the basic height and my geometry and my soil loading. So let's look at what we can do with this wall. And what we're going to look at first of all is if we decided that it wouldn't be concrete but it would be masonry, a 3 meter high masonry wall. So if I go to masonry and I say yes, I have masonry, it would turn around and say that it's sliding because it's a slightly lighter wall, and it is inner steel because it doesn't have any inner steel. If I go to reinforcement, we actually wouldn't have any reinforcement unless we were having pockets in that wall. Bear in mind that if we left reinforcement there, we would be assuming that we're using either pockets or hollow filled masonry, and that we'd have to make sure that we got the right masonry strength. So let's look at our masonry. Clay bricks, I don't think so. I'm going to go for concrete blocks, and I'm going to go for unit strength of at least 10.4s. Standard designation, standard group, standard execution class. So we're seeing that we're absolutely failing absolutely miserably as an unreinforced wall. So what can we do? Well, obviously a 250 wall is not the right size, and we can start to increase that to see how we go. So we would really need to go out to a colossal wall to make that work, and that's not going to give us any sensible values at all. So if I start with a 215 wall, I can now come along and say I want to step that, and I can say I want to step it and take off the outer, so an inner stepping. And even with the inner stepping, we're still finding that this is not a thick enough wall. So it's not going to be a solution that we want to use for a 3 meter high wall with no reinforcement whatsoever in the wall. And naturally putting reinforcement down here isn't going to help because you really wanted that lever arm out here in this case. So if we take off the stepping We can now go to our third type of wall, and that is the reinforced masonry wall. So what we need to do is go to masonry, ask it to have an outer leaf, and ask it to be a filled cavity. So we just need to look at our dimensions here, and we are going to go for 100, 100 and 100. So the wall is now going to be 300 wide, and then we have 100, 100 and 100. So 300 wall, and if we then go back to the masonry, we have an outer 100 and we have a filled cavity. Now again, let's look at our wall, and in this wall we're seeing that this is the most important. This is just the shuttering for the concrete. This is the compression zone. So we want to put in bricks or blocks that are going to work. So again, I'm going to stick with blocks, and I'm going to up this to at least, sorry, wrong direction, 10 Newton or 17 Newton. So we'll go for 10.4, a standard block. And we are obviously still failing miserably, but what we now can look at doing is putting in this cavity reinforcement. So it's automatically going to come down the cavity, but it is going to be pretty heavy. On a 3-meter wall, you would have very heavy reinforcement. So let's drop it down to 100 centers, and we're still well overstressed, so we would need to go to maybe 25s, and we're over our capacity. So what is our problem here? Interface wall, we just need to be careful that we're not just putting steel in and it's not doing anything, and the problem actually is the shear capacity and the moment capacity. So we just need to be careful of that. So my solution is going to be to extend the width of the cavity. So if I go to the wall and I make that 400 wide and then make the cavity 200, so we're going to have a far bigger cavity with our 100 and 100 block. We're looking at reinforcement that's not too bad, just under moment capacity. And the reason that we're having this heavy reinforcement is because of the bearing strength of the concrete, of the masonry. So if we think about that masonry, we say actually if we can get ourselves 17 or 22 Newton blocks, that's going to be your concrete strength. Those blocks are the compression component. So really we need to have good blocks or wider blocks. So back to reinforcement, and I'm quite sure I could get down possibly the 16s at 100, and we are seeing everything working. My inner steel's at 75%. That's a good value, and I could possibly then push that up to 150s to match everything else. We're now at 84%. I wouldn't really imagine I would go any higher unless I came to 12s and I came down. So 12s at 150 is again on the sweet spot for that reinforced masonry retaining wall. And again, that's how simple and quick we can take the exact same design and do an alternative to it. So we can do an alternative. And this has all been done to EuroCode 2, EuroCode 7, and EuroCode 6, which is described here as EN 1996. Possibly should describe those all as EC rather than mixing the designation styles. If we wanted to see, well, what would be the difference if we went to the British standards? So if I changed from that to BS and changed the codes back to BS and for the masonry to BS, we will see that to 8002, 5628 and 110, it is all still working. And what is our unity factors? It's probably actually slightly better to the BS rather than the EuroCode. So that's our basic 3 styles of retaining walls, just with a stem and a base. So what I'm going to do now is I'm going to go back, take off the masonry, and go back to I think it was 250 I was working with stem, and look at what else we can do to these walls. Well, the first thing we can do is we can go into our soil and we can work with a layered soil. So we can have a second layer and we could say let's work at the lower layer, and the lower layer is 2 meters high, so it's coming in at 2 meters high and it's laid at a 5-degree angle, and we can put in the density and consolidation of that layer. We can also then look even at the front soil to be a different soil. So we can have 4 zones of soil. We can have a front soil, the base soil, the lower back soil, and the upper back soil. So we have this 4 different types of soil that we can apply to the structure. So I'm going to come back to the back soil. We can also work from an analytical point of view with a virtual back. And with a virtual back, because we've increased the height here to here, and it's a sloping upper surface, we end up with a sliding problem. And the only way to solve sliding is weight. And that weight is going to be by taking, and it's a wee bit of a bit longer. I don't think we can actually improve it going the other direction because it doesn't make much sense because you're only getting the weight of the small amount of material. So 2 meters, so 2950, make that in this case 750. So if you want to go to the school of thought that insists on designing to a virtual back, we would need a slightly longer stem to prevent that sliding. Of course, that's if sliding is a problem. So if I went back to 1700, I'll leave that at 700, and it was actually 1600. So that's our rough wall size, and sliding is the problem. We got 2 other mechanisms we can use to resist that. We can naturally come along and say, we've got a prop. This is part of a basement or something, and it's going to have a physical prop here to stop it sliding. Let's just ignore the sliding. So we can just come along and say propped at base, and yes, that's it, done. We don't have a sliding problem, and we could probably, with the prop at base, reduce this, although we already have quite a reasonable bearing pressure width. If we don't have a prop at base, the only other solution would be to reinvestigate our site investigation and decide whether or not we have any cohesion in the base soil, and we could come along under soil data and put a 10 kilonewton per meter run cohesive resistance. That's going to give us 25 kilonewtons of cohesive resistance. Wonder would 1 work? No, it wouldn't. 2, 3, 4, 5, 6. So theoretically 6 kilonewtons per meter squared of cohesion. Not necessarily the cleverest thing you can do, but if the site investigation shows that it is a cohesive soil, then why not use it? Now, coming back to props, we also have additional props that we can do. We can have a prop at any level. So I can have a prop at 1500. So 1500, I could have a prop. So if this was a basement construction, we could say, well, we have a prop at 2.3 meters high, and then the basement, and then that's the retaining wall, and then we just build above that with normal construction. And obviously that changes the direction of the bending moment, so we actually have to have reasonable reinforcement in the outer face. So we need outer wall steel. 10s at 150 will cover that, and we could possibly, because it's propped, get away with our 10s at 150 on the other direction, and we might even be able to step down to 10s at 200, but I'm not going to repeat myself too much. And we can have multiple props, so you can have a 6 or 7 meter high double basement retaining wall with the props, and design that for yourself. There's no reason why you can't have a double basement with no heel whatsoever, but just a nice big long stem and a propped. The program will do all that for us. So that's propping, and along with propping we have the slightly more analytical tying, where we can say we have a physical tie that comes down here per meter run of wall of 10 kilonewtons, pulling back this. So it's quite very useful for you to be able to apply a tying force through the wall in those instances where you have ties. Wouldn't be my most popular solution. So that's ties. Running along here, we then have loading, and we've only looked at the base load of the soil and our standard, as we say, 10 kilonewtons per meter run of surcharge. We can add an additional surcharge. If I went 5 there, you'll see that that actually increases to 24 because it's 15 times 16. We can also do weird things like set the surcharge to only appear from the virtual back. Now that's not going to affect this surcharge, but it will affect any surcharge that sits back behind the virtual back, and that's going to tell you its total value as it goes back before it comes outside the line of influence of the soil on the structure. So dropping off my virtual backs and dropping off my additional surcharge, we can also, and it's very popular, we find, add in a horizontal surge force. So if we have a retaining wall, we can say that we want a 10 kilonewton surcharge at 850 high on that wall. So it will add in a kick moment of 10 plus, kilonewtons on that. So we have our overturning moment with our factors on that at the right top. So if I take off the horizontal surge, you'll see that the moment diagram now does not start at a value but at 0. So we can add this horizontal surcharge. We can also, if we decided, and this will have no effect at the moment, if I put 1 in there, it's got no height, so it's not going to do anything. One of the things we can actually do with the wall is that we can actually take this and we can add on another 500 of vertical height above the wall and apply that loading onto that wall as a wind loading and destabilizing the wall. And obviously then at detailing time we would have that additional load, that height of wall available to us to detail up that wall. So that's your virtual backs, that's your horizontal surge charges. We'll just drop that off, we'll put that back down to 0, we'll leave the wall sticking up. Somebody's asking me where's the bearing pressure, and I think under drop somebody's quite silly and set it not to draw it, but I think we should draw the bearing pressure. That gives us a better idea as engineers, keeps us in the loop, so to speak, so we know what is exactly happening. So just coming back to my loads, we also then can apply physical additional loads onto the structure. We can apply line loads, so we can say, right, we have a 10 kilonewton load at 800 mil away from the wall, from a lorry and whatever, and we then have another one coming along at an axle away 2.8 or whatever, So that would be 3600. So we are considering these two axial loads giving us increased bearing pressure and failure on the soil. And we can see the full effect of these point loads as they transfer into the soil and then are taken up and mobilized. And it's quite interesting. So we'll just keep it simple. I'll drop off those point loads, and then the other thing we can apply is additional loads. So I can apply additional partial UDL, and it's 10 and it's 17 and 6.5. One of the things we never talked about here was actually what type of load it is, and that would actually be quite significant in whether it's a dead load or a live load, because that would be quite useful to know from the loading point of view. Not that critical until we get into the highway loading on the structure. So we can apply these additional loads, so load coming in at about there all the way out to about here. So, and again, I can just drop those off, and now I don't have that additional load on. So additional line loads, additional partial loads, but the line loads are also quite useful in that they have the ability, and I'll just get rid of that second one, don't need its values either, and I can take this one, and if I put it in at 0, it's on the face of the soil, and if I put it in at minus 100, it's now on the wall itself. So if you look at what happens when I have it on the soil, you get this pressure. As soon as I take it off the soil, we get a slight change because it's no longer contributing to the soil. And obviously, as I move that onto the soil, we start to get its diagram kicking through and have an effect. And of course, this is because of the two different soils and the interaction between them, because they are different soils doing their things and getting a wee bit annoyed with this point load. So we can apply point load on the wall, at the edge of the wall, but we can also apply it outside as a destabilizing load. If this was some sort of retaining wall in some sort of factory or something, and you wanted to run heavy piping and the likes around and off the wall, then you could consider this. Or if you wanted to put a walkway along the wall, bolted on and halfway up the wall, then that would be able to be considered using this method of having a wall. And we can also pull it down. Doesn't necessarily mean that much in this. It does affect a wee bit of your loading on your structure where it's applied, because that's where the moment itself starts. The pressure is not affected, as I said earlier. So quite useful. I'm going to drop them all off, keep my walls simple. Let's look only at one item at a time. So I've been talking for half an hour, and I've more or less covered the basic wall types, the soil, props and ties, loading. Reinforcement, we've been working with it without talking too much. We can set the cover for the inner face, the outer face, and the base and nibs. We can set the tensile strength of the concrete if we want to consider that, the grade, and actually I would make that properly 500B, and the grade of concrete, and nowadays we're going to go for a grade 40 or a 3240 if we're dealing with EuroCode design. We're actually still in the BS. Let's go back to EuroCodes, and yeah, C3240, and we can actually just spin those up and down. So that's the basics. Now we can go into the what I would call the fantasy walls. The walls that I don't believe are very common, but we can do them. And one of the ones that's is asked for is the paired wall. Now we can do it paired with reinforcement, as we're doing here, and we can pop in what the reinforcement and the cover is and see how we're designing these walls. So we can actually say, right, we actually have a 250 wall, and sorry, and I'm going to make this 500. Get my mouse away from that little pop-up. And I'm then going to have it such. Sorry, I apologize. That's the top and that's the bottom thickness. It already knows the thickness of the wall. And I'm going to say it's 500. So it's a uniform pier. And since this is going to be concrete, it's going to be 300 wide. And we'll make them at 2 meters apart. And that these values are only applicable if we're into masonry. We have the effective outstands that we're allowed to consider. And we can say whether the pier is in compression or tension, which means we can move it to the either face of the wall. So pier in compression, then this is all my tension steel. I design it accordingly, or in this case pier in tension. And you'll see that it's giving us some relief in our wall, but not necessarily enough in this example with those additional loading I put on to the structure. So piers are available, and naturally those piers could be for a masonry wall. If I went back to the piers, we would see that this now is a masonry pier, and I can even step that so that we could have stepping it down, 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 down if we wanted to design that. As I say, these aren't, to my mind, the most effective ways to do these sorts of walls. Nowadays, it's far more sensible to do these in reinforced concrete and just to make them the normal thickness that you need to without having to go into masonry. So turn off the masonry, and then I would just solve the problem. So piers are also available. Now, the final thing I have available as a feature is something we introduced, I believe it was this year or last year into the program, I can't remember which, but that is the ability to design to the highways. Now this applies to the UK BD 3087 and BD 3701, so that means that we will be working with BS and BS for our design codes, and also BS. Well, actually be working to 5400 for the concrete part if we have concrete. Even though I say that, I'll just say highways and it pushes me back in. So it'll be telling me in my design when I get there that I'll be working to 5 structural design, and it'll be to 5400 rather than to 8110 with a gamma factor of 1.1. So I can come along, and I've now got an additional tab for my highway loading, and I can see the factors that I use for the 1, 2, 3, 4, 5, 6, 7 loading cases that are required under DB 3701. And then I can go to my loading, and when I go back to my loading and I put on 2 line loads as I had previously, and I'm going to put this line load at 900 and I'll put its friend at 3600 and make it 10 as well. We can now say what the load is, and not just dead or live, but whether it's HA, HB, or a construction style loading. So loading from vehicles during construction, or HA and HB. So if I say it's an HA load and this is an HA load, then that will use that accordingly during the design. So we have that full facility, and again it'll be HA, BHB or construction now that we're using highway loading for our additional loads. So we can do those highway loaded retaining walls. We can also in the highways do bridge abutment loading. So I can look at putting bridge abutment loading, and it's a similar to the normal point loads, but these are specifically on the bridge abutment. And I will see that I actually then have them as a classification on the loading, which is quite fancy. So I can say whether it's a accidental wheel load or whether it's an HB load or a wind load. And these are all the classifications out of the BD. And that allows me to say I have a bridge abutment. Well, it's a bit skinny to be a bridge abutment, but let's put some load on anyway. 500 kilonewtons in the Y direction at 400, and it's going to be a type HA load. So we do have that flexibility. I am not an expert in highway design, so I don't know what loads I should be putting on, but all the loads are here for you to use, and it's very straightforward. And you will see, as we had a quick peep, that we get our geotechnical design with active earth pressures when we're in highways, and then we have at rest earth pressure for the actual structural design. So the geotechnical and the structural in highways are using different soil pressures, and then we're coming down, it's giving me my prop resistance, my inner steel, my bottom steel, and my top steel on my design. So all the calculations are all done for you on your asking me about the CAD output. And that's a very good question. If I come back, take out the masonry, come back to concrete, it's far more sensible. Concrete wall. I'm not going to worry about the fact that it's failing. But we have the ability. Clearly you can print, and you can print it to a printer, and I'm going to print it to a PDF writer. And what's happened is it's spat it out to our writer, but it's sitting there in the repository. So if you wanted to go and do something else on this document, you could add that in. But I'm happy, print that, off it comes. I don't need that new version. And just say save, usual place, document in documents, replace the old one. And here we go. And we have our little retaining wall with our output of our calculations. Now that's one way of doing it. The second way is to go to our exporting tab. And in our exporting tab, we can give you a set of details. So the wall reinforcement, we're going to use U-bars and straights. So we could even say we're going to use asymmetrical U-bars, or we're going to use asymmetrical L-bars or L-bars. Let's go for U-bars and straights because we don't want it to go up too high. And we're going to put a U-bar at the top, and we're then going to have the base to be U-bars and straights. So U-bar and straights in between. We also have, for those shorter arrangements, and it will tell you if it gets too long, top and bottom U-bars, so they're pointing up and pointing down, or open links with a closer, and we will just accept the standard U-bars and straights. So we set a length that's into the page of wall, and we can do anything up to our 12 meters. So I'm going to go for a 7.5 meter long wall, and we're going to have some offsets for our reinforcement, and we're going to have a wall kicker of 150, going to give it a good high kicker. So we'll start our lapping of bars above this kicker point in this, and I'm just going to say export to DXF and load AutoCAD. Off it goes, replacing the existing one, loading in AutoCAD, and what we now have is our wall drawn here and our wall labeled up on this one and labeled up here, and that is for the 7.5 meter length. And yep, there's your little, that's your plan view, and there's your starter bars on plan, and then there's your two main bars, and then on the front view you'll see the starter bars coming up, so that we have in here these bars starting above the kicker point. I asked for 150 kicker, so these are starting at the 150 up and are detailed accordingly. So just close that down, won't save it, but what I can also then do is produce a little drawing schedule that matches that DXF drawing, and that's all your reinforcement in that wall. And you should see that our bars, the lacer bars, are 7/400 because we asked for 50mm cover on our wall. So that's all very, very straightforward, very quick and easy to do. And we can also do the same, not to DXF but to our MasterRC program, and get the exact same drawing that we could then edit. So ladies and gentlemen, I seem to have used up the whole hour by going through quite a lot of different questions. I'll just see if there's one more question, and then I will show you how you would change your national annex values. And yes, somebody asks me as saying that sometimes the output will say that less than 20% of the base is under pressure. That's just a common sense warning. It's a rule of thumb, but I think it's quite a wise rule of thumb to say that you don't want a wall that's constantly got uplift here, because if the wall's is going to rock and it's going to suddenly loosen the soil here with this being on pressure and that being in having no pressure, and you are going to slowly over time get that wall tilting. So it's not a good idea to have a wall with a lot of uplift on it. So I said I would show you very quickly how you would go in to your national annexes. So utilities, customization, and we go to design codes. So here we have our design codes. We've got the default, the Euro norm, the vanilla flavored EuroCode, and we also have by default the UK values. You can add in your own one. We'll call it George, not to be confused with anybody else. So this is George's. George is going to base his on the UK version. So he's now able to go in and say for actions on structures, partial load factors, we want to apply these values for partial load factors for snow, temperature, categories, and the side 1s, side 2s. So if you know your codes, you can change those. You can see that we're using 0.925 rather than the BS 0.85, I believe, for this little factor, and that is what gives us the change in capacity of 1.25. So you can go in and you can change any of these parameters as you require. In the geotechnical itself, you can see your actions and your gammas, and you can change those, and those would change your load combination values in your retaining wall design. So ladies and gentlemen, it only goes for me to say thank you very much for coming along. You've all been very patient listening to me, and if you aren't a user and want a free trial of the software, just log on to this website and ask for a free trial.